Hola, muy buen día. Muchas gracias por esta invitación. Es un verdadero honor estar aquí con ustedes en Chile. Gatherings like this of knowledge in Congreso Futuro are really proof to me that society wants to advance, wants to explore. And one of the ways that you see that is really in space. Perdón, ¿dónde está el monitor? Ahorita va a salir. Un momentito, ahorita va a salir. Okay, ahí está. So, we know as a society we want to explore space. We've learned that when we wanted to go take humans into space, we built big rockets. And we realized that if we wanted to go even further, we needed to go to small probes, things that would allow us to go much further than our human bodies would allow. And this shows you 65 years of exploration that we've done. We've sent 72 missions to the moon, 38 missions to Mars. And if you go out even further into the outer planets, you see that we've only sent a handful of probes. But if you look out even further on a cosmic scale, we haven't really been anywhere. One of the farthest human-made objects we've ever made is Voyager 1. Sent out in 1977. It would take us about, if we were to look to how long it would take us to get to the nearest star, it would take us 10,000 years with any type of propulsion that we can think of today. And so in 2016, scientists from around the world coalesced around a really bold idea. The idea was to send lightweight sails to carry a microchip probe. Microchip probe containing communication systems, cameras, sensors. And the idea was to leverage the great advances that we've made in nanotechnology, in lasers, and also in material science to go further than we've ever been before. And so the idea was to attach small microchips to very low mass sails, about meters large, that are about 1 gram in weight. And the idea is that with about 10 minutes of laser exposure, if you can get this down to 1 gram, we can accelerate these sails to about 1/5 of the speed of light. And these type of materials, these type of sails would allow us to make the 10,000 years into something like 20 years. And it's really amazing to think that a material would allow us to do such things. And so if you look at what that really means, think about what that means. A 4 by 4 meter sail that weighs about as much as a paper clip. It's something really very different than what we are used to. What you're talking about is something that has something about the thickness of a bubble, or about 1,000 times thinner than a human hair as a sail. So, a lot of people agree that the sail is actually one of the biggest challenges of this mission. And why is that? Well, if you look at the microchip basically requires that we miniaturize everything in X, Y, and Z, making everything smaller. But this is something we've been doing for the last 50 years. But the sail is a very unique nanocomponent because it's the only one that needs to be expanded to meter scales. Okay, and it's a very different type of miniaturization. And so this is a very different type of nanotechnology than we've ever made. And the idea is that it's not just big and expands to meter scales, but it also needs to be covered in billions of nanoscale features. This is very different than any material that we've made in science before. And so what my lab has been doing, and many labs around the world actually have been also looking at, is how to use these materials for mechanical sensing and optical computing. So how do we make such a thin sail into a very high reflector for lasers? Well, if we take a 200 nanometer thin sheet of ceramic and you were to point a laser at it, you would get it would reflect about 30% of the light at many wavelengths. But using techniques that we use in the clean room, we can make millions of nanoscale holes. And counterintuitively, we can actually make this into a very good reflector by putting holes into it. So when the laser comes in, these holes, the light sees a completely different material because these holes are smaller than the wavelength of the light. So it's a completely new material that reflects at almost 99%. And this also reduces the weight quite dramatically. And so in my lab, we figured out that not only are these materials very reflective, but they're also extremely strong, which sounds strange for something thin. But what we've shown is that these materials can take stresses or tensions of 1 gigapascal. And to give you a sense of what that means, it's essentially the same as taking duct tape and hanging about 2 or 3 cars off of it. So how is that possible? Well, how that's possible is that if you look at materials in our everyday life that are big materials, it has a lot of small defects, a lot of small little defects. So when you pull on it, this is where breaking and cracking can happen. But as you make these materials thinner and smaller, there's almost very little chance that you have such defects. So it means that you can actually approach the ultimate limit of materials. And this is something very counterintuitive because you think as you make something thinner, it becomes more fragile, but that's not what's happening here. So here, just to give you a sense of real sail materials that we were making in our lab now, this is a microscope image of what such a sail looks like. It's 200 nanometers thick. It's covered in holes. And just to give you a sense of scale, this would be a human hair, the radius of a human hair. Now, if we zoom out even further, this is the sail material, this is the frame, and this is the holes that we were just looking at, so you can see that it's part of a bigger tapestry of holes. And here again is the human hair for a little bit of scale. If you zoom out even further, you see that it's part of thousands of holes. And if you zoom out even further, you can see what are the biggest light sails that were available in 2016 when this mission was announced. So this is about 1/3 by 1/3 of a millimeter. Okay? So these are really the biggest things that were available about 10 years ago, exactly 10 years ago. So let's look at this again. Well, we were talking about meter scale things. This thing is about the size of a grain of sand. So how is it possible? And even if you look at these large meter scale sails, what you find is that it would take almost 25 years just to make all those holes. 25 years just to make the holes in one sail. So it seems really large, but what we've done in our lab is for now the last decade, we've been working very hard in the clean room to figure out new techniques, new ways of manufacturing these sails. We've been looking at the mechanical properties of these sails to make them stronger and so we can fabricate these things. And we've also had a lot of broken materials. But what we see here is these are now the largest sails that we can make in our lab. What you see there at the arrows are the sail that I just showed you. So we can now make these about 60,000 times larger than was possible before. We can make them about 9,000 times cheaper, and we can bring that 25 years down to 1 day with new techniques that we've developed. And so recently, we've also figured out, using high-powered lasers in our lab, that these type of materials can actually withstand optical intensities that you would see at the surface of the sun. So this is really, really a very special material, very thin material that can take such optical intensities. But what's actually possible today with what we have today, with what we can make in the lab? Because meter scale things are really quite a different thing. So these are all the different silicon wafers that are now available today. Since the 1975, the biggest wafers we can make today are about 450 millimeters. How long would it take to get to the next star, Alpha Centauri? It would still take us, even with the largest wafers we have, it would still take us 200 years to get to the nearest star. But if we were to start thinking about Voyager, the one that went out in 1977 and took almost 50 years, how long would it take to get to that position near the edge of the solar system? Well, then it gets very interesting, because now you're not talking about 50 years anymore. You're talking about maybe 38 days instead of 50 years to get to the edge of the solar system. And what if we start to think even closer within our solar system? Well, then it gets even more interesting. So here, this shows you all the fastest flyby probes that we've gone to every single planet. So for Mars, the fastest we've ever gotten there is 4 months. For Saturn, it's about 7 years with Cassini. And with the sails that we can make today in the lab, we can bring these times down to hours and days instead of years. And so, for instance, you can imagine going to Mars in 32 hours, sending chips there the way that we send international mail, or sending chips into the oceans of Saturn's moons, Titan, in less than a month rather than 7 years. And so what you see is that these type of materials start to really change our reach in the universe. And if you even look at Voyager, we're now looking at, instead of nearly 50 years, 1 year to get there. And so what I want to say here is that these materials can really change how we expand in the universe, how we touch other planets. But not only does it change our reach in space, but it can also reach our reach in time and how we consider time. So imagine that you were on a swing and somebody pushes you, and without anything else, with so little energy coming out of the swing, you could swing for 100 years. It sounds crazy, and it sounds like something that would never happen in real life. But really think about what that means. Imagine that 100 years ago, in 1926, I put a 3-year-old on a swing, I give him one push, and he continues to swing and swing until the age of the first space age in the 70s. He's now 53, and he's still swinging. And even then, he's still swinging, because there's almost no energy lost through those ropes until he's swinging up until today. And so that sounds like something that's really impossible in our everyday world, but at nanoscales, when you can use these new materials that we have, we can actually make such things possible. So let me show you. So now these materials we've now made into small little trampolines. These same light sail materials, we can make into these small trampolines filled with holes. And the idea here is that these things are so thin and so long that they almost dissipate and they almost release almost zero energy when they're vibrating. And when it's hard for energy to get out, it means that it's also very hard for noisy energy to get into your system, into your sensor. So we're now using this as a vibrational sensor. And the idea is that this actually allows you to make some of the best mechanical sensors in the world today. So what does that mean? What can you actually sense? Well, what we find is that we can measure something on the order of attonewtons, 10 to the minus 18 newtons. What does that mean? Because we don't think about attonewtons in our everyday life. What does that actually mean? It would be equivalent to the gravitational pull between two people, the tiny gravitational pull between two people, which are 1,000 kilometers apart from one another. So you can imagine this is the gravitational pull between one person in Santiago and one person in Antofagasta. So these are really completely new types of sensors that we can make with these. So what do we do with them? So with collaborators from Sweden and Korea, we're now looking at whether we can use these for earthquake detection. So right now, when earthquakes happen, the way that we know is that the vibrations take some time to reach our house, and our house is shaking, and that's how we know, right? And that's not very good. But what if we could measure the gravitational change of the Earth when an earthquake happens, when the sudden movement of the crust moves, and you can measure the gravitational change in that? It's not science fiction. This has actually already been done with the large earthquakes in Japan. We can actually measure the gravitational changes of the Earth. And what that means is that you're getting the signal not at the speed of the vibrations, but at the speed of light. Gravitational forces move at the speed of light. And that means that you can gain maybe 5 seconds of warning. And that doesn't sound like a lot, but it's an infinite amount of time if you're thinking about crucial operating rooms that need to shut down machines, or crucial infrastructure that needs to be shut down immediately. And it's the difference between a meltdown and a safe shutoff. And so what I want to say here is that this type of nanotechnology is going to open up new types of physics that we're not familiar with at our large scales, new types of engineering. It's going to allow us to look at the universe in a different way, expand and explore it. It's going to allow us to look at ancient challenges like earthquakes, things that we've been dealing with for millennia. And we can do this with nanoscale materials now. Now, this is not a new thing. Actually, in 1959, the great Richard Feynman, when he was first describing nanotechnology before there was nanotechnology, he made the prediction that as things get smaller, things like weight and inertia would have almost no importance, and that the strength of materials would be much, much greater. So this isn't a new idea, but what is new is that now we have the technology to really take this idea to its extremes. So I want to thank you for your attention, and thank you again.